So we're going to kind of jump into the next topic, which is confidence intervals. If you have any questions along the way, like this is going to set up a lot of stuff that we're going to talk about. We're going to be doing confidence intervals probably the entire week, maybe even a little bit next week, and then that kind of leads us into hypothesis testing. So we'll make sure we have a really good understanding of kind of what we're doing. So I'll probably go through quite a bit of stuff that's not in the slides, hopefully to give you a slightly better idea of kind of what we're doing with this, right? So the very first thing we want to think about is, last week we talked about dealing with the distributions of different sample statistics. So the sample mean, the sample proportion, right? So the whole reason, we were going through that is to set up this idea that we usually can't see what the population mean or what the population proportion is, right? In the examples that I was giving you, I was telling you what the population mean and population proportion were just to prove to you what is going to be true about those distributions, right? But once we know that that's true, even if we don't observe the actual population data, that's okay, right? We can still do some things that give us a lot of power to make some pretty useful statements or powerful statements. So what we'd like to do is hope that these sample means, and everything I say here, I'll be using kind of means, but it's really any parameter. So everything I say about means applies to proportions as well. Remember, we kind of mentioned proportions really just the mean of a 1-0 variable. So every time I say mean here, the same would hold for the population and sample proportion as well. So we get this sample mean, or we take a sample, but that's all we can see. We hope that that sample mean is predictive about what the population mean is. Like, let's say I took a sample of 40 people. I see a sample mean for income of 45,000, right? Well, the true average income in the US could be only 40,000, right? My sample could be off because there's a distribution for those sample means, right? If I'm just taking one sample, I can only see one value. Well, I'm only seeing one part of that distribution, right? Now, there's some values that are more likely or less likely than others, but I still could end up with being pretty far off of what that true population parameter is. So we already talked about what are we going to try to do is get a sample mean that's unbiased as possible, right? We talked about making sure that the sample reflects the population. You have a selection or non-response bias. We also want to get a really small variance for our sample mean distribution. So the idea behind that was, if I have something like this, so I'm thinking about the distribution of my sample means. If I can get something, right, that has like a really, really peaked distribution, right? So low variance meant that it's very likely that if I take one sample, values near the mean are very likely for me to see, which is good because I'm only getting to see one sample mean. Also, values farther from the mean are going to be way less likely for me to see if I can get a really low variance on that sample mean distribution. Right? So this is kind of what we're trying to do is we want to make sure that we're seeing sample means that are really close to that population mean. Okay? So the general setup of what we're going to try to do, it doesn't matter if it's a population mean or population proportion, is we're going to take a sample, right? It's the only thing that we're only going to have one. We'll then calculate what that sample statistic is. So for this case, I'll kind of say sample mean. And then we'll use that sample mean as this is the best evidence we have about what the population mean is. So from this sample mean, I'm going to construct a range of values that I'm telling you with a certain level of confidence, the true population mean is somewhere in this range. So for example, if I took a sample and I see the average income or mean income is 45,000, well, I know I'm probably a little bit off. I would be, the probability that I see a sample mean exactly equal to the true population mean, well, remember, the probability of any one value, if it's a continuous random variable, is 0. So the likelihood that I'm not getting the exact value is 100%, right? It'd be almost impossible for me to see from my sample the exact population mean. So I know I'm going to be a little bit off. So what I say is, okay, I see a sample mean of 45,000. Well, I feel pretty confident if I use that sample mean and then said, well, I feel pretty confident that the true mean is somewhere between 40 and 50,000, right? Because that's a pretty wide range of values centered around the best evidence I have of what the population mean is, which is just my sample mean. And I'd feel a lot more confident giving you that range of values than say the true mean is probably somewhere in this range. But how do we decide what that range is? So what we're going to do, and this is, I'm not going to use this example, so I'm going to skip this slide. I'm going to change things up a little bit today. So what we're going to do is whenever we see our sample mean, we want to build this range of values around it for where that true population mean lies. So when we do this, we're going to go a certain amount above and a certain amount below whatever the sample statistic we see is. So it's going to look something like this. Right? And I'll go back to the previous slide in a second. So we're going to take that sample mean, go a certain amount below it, and go the same amount above it, and that will be what we call the upper and lower bound of our confidence interval. We're then going to use this range of values and say, with a certain level of confidence, based off of the sample mean I found, right? That's what I'm basing this confidence interval around. The true population mean lies somewhere in between these values, okay? So we're going to be able, when we build these confidence intervals, we're going to have different confidence levels we can make, right? If I wanted to say that with 90% confidence, so let's keep running with this same example. With 90% confidence, I can say that the true, if I saw a sample mean of 45,000, with 90% confidence, I'm going to say, well, I'd be okay, you know, I can say with 90% confidence that the true mean is somewhere between 40 and 50, right? So if I'm able to say that with 90% confidence, how could I say something with 95% confidence? What would have to be true about the 95% confidence interval? If saying it's between 40 and 50,000, I can say that with 90% confidence. What would have to be true about the range of values if I wanted to say something with, say, 99% confidence? Yeah, I have to include more values, right? I mean, if I include smaller values, how the hell could I say it was 90% confidence when I have this range, but 99 for a small range, right? So to be able to say things with higher levels of confidence, we're going to be thinking about, well, we're going to have to give a wider range of values here, right? But how far out do I go, right? How did I even choose that I was going to go out 5,000 from my sample mean? Well, it's not arbitrary to what values we're going to choose. There's actually like a method behind how we actually choose how far away we want to go from our sample statistic. So that's going to relate to, like, how do we choose this W, right? So that's going to relate to what we talked about last week, okay? We know the sample mean is normally distributed, right? So we can use this normal distribution to our advantage. Right? If I say one of the 95% confidence interval, you can think about it, and this isn't technically maybe quite correct, but to set this up, think about it this way. I've built this confidence interval, and within this interval, right, I can think about there's a 95% chance the true mean is somewhere in that interval. Which means the probability that it's outside of that interval would be what? The probability that the true population mean is somewhere in that interval is 95%. The probability that's outside that interval would be, or the percent chance that it would be outside that interval would be 5%, right? Or a probability of 0.05. So really what we're thinking about there is, if I know that the sample means are normally distributed, and not only do I know they're normally distributed, I know they're normally distributed around that population mean. So I know there's a 95% chance that I will see a sample mean somewhere between 1.96 standard deviations below and 1.96 standard deviations above. Why do I know that? Well, if I think about, if I want the area in between the two values I'm looking at to be 0.95, that would leave me kind of 0.05 outside of that range, or 0.025 on each side, right, in each one of these tails. So, oops, I want to keep that big though as I switch back. If I want the area in that lower left tail to be 0.025, and I go down here, what z-score would give that to me? So 0.025, that's the area I want in the tail. That's my probability in the tail of seeing that z-score lower. Negative 1.96, right? So really what I'm thinking about there is, if I had this distribution of sample means, if I could observe, if I didn't just have to take one sample mean, but I can see a bunch, I know they'd be normally distributed around this population mean. And I know that if I went down, well, actually I want to do it, here, I'll do it this way. So if I went, if I went 1.96 standard deviations below whatever that true population mean is, the probability I see something that far away or even further away in that direction is 0.025. And where did that 1.96 come from? Right? Well, if I know the area in the tail I want was 0.025, I can look it up in the table, find negative 1.96. But remember, z-scores represent the number of standard deviations away from the mean. If I know the sample means are normally distributed around that population mean, then the actual kind of cutoff value I want for my lower bound is whatever is 1.96 standard deviations below that mean. Right? So kind of thinking about whatever level of confidence we wanted, the way we say, if I want something with 90% confidence, what I'm really saying is when I go a certain number of standard deviations above and below the mean, I want the area in between those values to be 0.9. If I want to say it with 99% confidence, however many standard deviations I go above and below the mean, I want the area in between those two values to be 0.99. Right? And then if I know the area I want in between, I automatically know the area outside, right? Because the area under the curve is 1. All I have to do is subtract that from 1. Now I've got two sides here, or two tails. So I know that the total area outside of this range, right, each tail will have half of it, okay? So using that idea, we can then think about, okay, so I know that this is the distribution. I know that I'm kind of look these z values up, and what number of standard deviations above and below the mean would give me 0.9 in the middle, 0.95, 0.99. And these are kind of the benchmark values we use. But we could use whatever value we want. We could use 0.83, right? We can do whatever we want, okay? But 83% confidence is kind of a, just it seems weird, right? Benchmark of 90, 95, 99%. So if we think about this distribution, right? And I'm still looking at that 95% confidence interval, okay? So I go 1.96 standard deviations below and above the mean. I know that if I took a sample and I see this sample mean, okay, I then build a confidence interval around that sample mean. So I go 1.96 standard deviations, and notice this is the standard deviations of my sample means because that's the distribution I'm looking at. Right? If I see this sample mean and then add 1.96 standard deviations and subtract and build a confidence interval around it, notice my confidence interval here contains that true population mean. And I try to draw this to scale, but if I saw another sample mean, but let's say this time I see a sample mean that's higher, right? I build my confidence interval around that sample mean. Notice it also includes that true population mean. If I see a sample mean anywhere in this blue range, when I build a confidence interval around it, it would always include that true population mean. Okay? And you can kind of get the visual here. You might say, how's the math work? I don't know if we'll get there today, Wednesday for sure. I have an example in Excel that I'll kind of hopefully prove this to you a little bit more. Okay? But for now, just take me at my word. Okay? Now, sometimes even though the likelihood I see something outside of this range, right? There's only a 5% chance, or the area kind of outside 1.96 standard deviations above and below is only 0.05. If I did see a sample mean in that range, notice when I build a confidence interval around that sample mean, it doesn't include that true population mean. But I know that that's only going to happen 5% of the time because I'm only going to see a sample mean value in this red range 5% of the time. Okay? So, said differently, if I took 100 different samples, 95 of those 100 different samples, each one calculated the sample mean and build confidence intervals around that sample mean, 95 of them would include the true population mean, 5 of them wouldn't, right? Or that's why I'm saying with 95% confidence, if I'm only able to observe one sample mean, with 95% certainty, it should include that true population mean, right? It'd be great if I could take 100 samples or 1,000 samples, but a lot of times we only have one, okay? And so this is kind of what we're stuck with, right? We can say things, but not with 100% certainty, only with like 95% certainty, 99, 90%, whatever level we choose. Okay? Any questions on this before we keep moving? Just kind of making sense here. So what if I wanted to do instead a 90% confidence interval? What would I do here? So with a 90% confidence interval, what I'm saying is I know that 90% of my sample means, if I built confidence intervals around them, would include that true population mean. So I'm thinking about, I want to go a certain number of standard deviations away from that mean, such that the area in between is 0.9. Okay? I'm going to use a different color too. I think this marker's dying on me. Hopefully this shows up well. But I know that if I have the area that I want here being 0.9, what has to be the area in my tails? Total area. It's not a trick question. Yeah, the area in between these two values is 0.9. The area outside of those values is 0.1. Well, I have two tails. So because this is a symmetric distribution, and I'm going the same number of standard deviations above and below, what I'm really doing is the z-score represents the number of standard deviations away from the mean. So I'm going to go the same number of standard deviations above and below whatever that mean is. So I'm going to be looking at the same z-scores. Because this is a symmetric distribution, the area to the left of the negative z-score is the same as the area to the right of that same absolute value, but a positive z-score. So if the total area in the tails is 0.1, how much is in each tail? Yeah, just half that, right? So whatever area you want in the tail, you just divide by 2, right? And we know that the area that we would want there is 0.05. Well, if I know the area I want in the tail, and I want to find what z-score would give that to me, I just go to my tables, maybe. There we go. I say, I know the area I want in the tail, so I'm looking up a probability that I want in that tail, right? So I'm looking up values in the middle. I'm trying to find 0.05. Looks like I'm in between these two values. So in between a z-score of negative 1.64 and negative 1.65. We'll take the higher of the two, negative 1.65, right? So we know that if we want 1.65 standard deviations above and below that sample mean, above that population mean, 90% of the sample means we see would have a confidence interval that includes that true population mean, and then 10% wouldn't. Right? So remember when I said, if you want to go say something with 90% confidence, if you want to say it with 99, you'd have to widen the range of values. Well, this will actually prove to us the same thing, because if I want to have an area of 0.99 in between the two cutoff values I need, well, what has to be true? If the area in between was 0.9, well, you can imagine. If I go here, right? The area in between here, if that's 0.99, what's the value of our, what's the probability I see something outside of that range? Probability I see something in that range is 0.99. The probability outside that range is 0.01, which would mean the area in each tail would now be 0.01 divided by 2, or 0.005. Well, now if I look up 0.005, it's a smaller area in the tail, so it should be that, you can find it, negative 2.57 and negative 2.58. So I'd have larger z values, which essentially would kind of widen that interval, right? It pushes, it's moving further away from that mean of 0 from my standard normal distribution, okay? So this is kind of the idea behind what we're trying to do. I want to take it one more step, and then we'll kind of have completed what we're doing here with confidence intervals. So one more thing before I kind of show you the equation for confidence intervals, just to kind of clarify. So I've been kind of mentioning you can say things with 90, 95, 90%, whatever percent level you want. These are just kind of the benchmarks that we use. If I'm looking at the 90% confidence interval, we'll start referring to this thing called alpha. I would say you can think of alpha in one of two ways. essentially alpha is the area, the total area in the tails, or the total kind of, the probability I see something outside of that confidence interval. Right? That's really what it represents, right? An easier way, maybe less technical to think about it, is whatever my confidence level is, like let's say I have a 90% confidence interval, well, what percent is outside the interval? 10%? Well, alpha is that percent of being outside the interval in decimal form, right? 90% confidence interval, 10% would be outside of it in decimal form, 0.1, that's your alpha, right? But that really is related to what we were doing up here on the board, right? We were just kind of first converting the confidence level, 90%, into a probability of 0.9, and then now the probability we see something outside the interval was 0.1. Right? So just two different ways of thinking about that. Like I said, the less technical way that's, I think, kind of easy to remember is, alpha is the decimal form of whatever percent is outside your interval, right? So for 99%, the area outside the interval is 1%, decimal form, alpha is 0.01. And you can work in either direction, right? If I told you what alpha is, you could tell me the confidence level, right? Because if I told you that alpha is 0.05, well, that's the area not in my interval. So the area within my interval is 0.95 or 95% confidence interval. Right? So that's just some I don't know, not notation, but kind of making sure we're all familiar with this terminology. So what we're going to do to build this confidence interval is choose this lower and upper bound to where I can start to make statements that I can say with 90% certainty that the true population mean is somewhere within this range. Okay? We'll build it around our sample mean, so it'll be centered around that sample statistic we found. We will then go a certain number of standard deviations above that sample mean to get the upper bound, and we'll subtract that number of standard deviations from our sample mean to get our lower bound, right? So this is essentially, you could write this out as two equations. This plus minus is really just telling you when I want the upper bound, I add this. When I want the lower bound, I subtract this, okay? Sometimes I'll refer to this, and it's more appropriate to refer to this when dealing with proportions as the margin of error. So what I'm adding and subtracting to my sample statistic, I'll kind of refer to it as our margin of error, right? Now, we're going a certain number of standard deviations away from that sample mean, and how did we choose how many standard deviations that should be? Well, when we were here, right, the area in our tails was 0.1, that was our alpha. Well, before we looked up the z-score, we didn't look up 0.1, because remember, 0.1 was the total area in the tails, so there was half of alpha in each tail. So what we really did here was look up the z-score. These both look like alphas, hold on. What we really did here, I can't draw two. There you go. Was look up the z-score for alpha over 2. Right? That's really what we did. Okay? So in that equation, that's why we have, we're going to add to that the z-score for alpha over 2, right? Or go this many standard deviations away from that sample mean to get whatever the desired confidence level you want, because alpha will always correspond to a confidence level. Alpha of 0.1 is confidence level of 90%. Alpha of 0.01, confidence level of 99%. Right? Alpha of 0.2 would be a confidence level of what? Alpha of 0.2, so alpha represents the total kind of area outside of that interval you're looking at. So that means the area within the interval would be what? 0.8 or 80% confidence, okay? So that's how we can think about this. Now, one thing that kind of complicates this a little bit is, what's the standard deviation of my sample means? Remember from last class, might have been 2 classes. No, I think it was last class. The standard deviation of our sample means is the original variance of whatever data we sampled from divided by our sample size. Okay? So, with that in mind, right, what are going to be some things that will change our confidence interval? Well, I kind of already have mentioned this one a few times. But if I go and I want a larger alpha means I have a higher area in those tails. So if alpha goes up, or the area in my tail gets larger, what's going to happen to that z-score I'm using? All right, if we think about this visually, if I have a normal distribution, remember we said we're looking up the z-score for alpha over 2. So if let's say I first start out and I have an alpha of 0.1, right? Actually, I'll go, let's say larger alpha there. So let's start out, we have an alpha of 0.01, which means alpha over 2 would be 0.005, right? If I then go to an alpha of 0.1, well, now the area I want in that tail, alpha over 2, is 0.05. So whatever z-score I had before, when I want a larger area in that tail, what has to happen to my z-score? It has to move out this way, right? So it's getting closer to what value? Remember, we're dealing with standard normal distribution, so it's getting closer to the mean of z values are always have a mean of 0, right? It's the whole reason we were using that standard normal table. We converted these originally normal variables into a standard normal with a mean 0, variance of 1. So we know that the z-score is going to have to get smaller in absolute value, right, closer to 0. So if I go to higher alpha values, my z value is going to get smaller, closer to 0. So what's that going to do to my confidence interval? Well, if I go back here, if that z-score gets smaller, what happens to my confidence interval? I'm adding and subtracting a lower amount to it. So I'm going to get a narrower or a smaller interval. Right? And that makes sense. If I want to say something with, if I'm moving from saying something with 99 to 90% confidence, well, that's actually my alpha getting larger, right? As I say something with lower confidence, the area in my tails or that alpha gets larger. Okay? And so for a smaller level of confidence, I'm going to have a smaller range of values. Right? What's the next? So we kind of went over that one. What about if I have a larger sample size? Okay. So if I have a larger sample size, just intuitively, when we've been talking about the distribution of sample means, what's that going to do to my distribution? Well, remember, the standard deviation of my sample means is equal to this. So when I'm talking about building a confidence interval, I could actually rewrite the equation as this, right? Because I was going a certain number of standard deviations away, but what standard deviation? The standard deviation of that sample statistic I'm looking at, which is the sample means. Okay? So if I have a higher sample size, what happens to, right, the standard deviation of my sample means? Higher sample size would do what to this? Higher denominator reduces that, right? Taking larger samples kind of lowered the variance on my sample mean distribution, which if it lowers the variance or standard deviation of my sample means, it's going to make this smaller, right? Now when I go the same number of standard deviations away, right? Even if I keep the level of confidence the same, I can say things with the same high level of confidence, but I can say it for a much narrower range of values because the standard deviation gets really, really small as I take higher samples, right? Because it kind of makes sense, right? If I was taking samples of size 1 or 2, this was the idea that we could still see really extreme values. Whereas if I take samples of size 200, well, I'm going to like average out all those extreme values, okay? So increasing my sample size allows me to keep the same level of confidence, but say it for a smaller range of values, which is what we want to do, right? We want to say, based off the sample mean I saw, with 99% confidence, like let's say use the income one. I see an average income of $45,000. I want to be able to say with 99% confidence that the true average or the true population mean income is in between, you know, $44,999 and $45,001, right? I want to be able to get to that point. And as I take higher samples, I start to get closer and closer to be able to say things like that, okay? Now, the other thing that's out of our control, I just mentioned before we went to the slides, if the original data just has more variation in it, what's going to happen to our confidence interval? So if the original population variance goes up, what's going to happen to our confidence interval here? So this guy goes up, and we're adding and subtracting a larger value, so our interval would get wider, right? If the original data has a higher variance to it, it's harder for us, based off one sample, to pinpoint kind of down this range of values where the true population, I don't have it anywhere, where the true population mean could be, okay? So we can't change that, right? We can't change the original data's variance. What we can change, we can change the level of confidence we want to say something with, but if we want to maintain a high level of confidence, the only thing, like, I guess, as researchers or us, you know, kind of work in this, we can only change our sample size. Go out and get a larger sample, okay? All right. Okay, so that's kind of all summarized right here, right? So one thing about the three components that we really have going on here are the z-score, whoops, that we look up, which is directly tied to whatever level of confidence we want. Within our standard deviation for our sample mean equation, the other two components, the original variance of the data we sampled from, and our sample size. So those are the three kind of moving parts we have here. So let's work through an example and put some actual numbers to this, okay? So the first example we have is, let's say hockey pucks, the weight of the hockey puck has a variance of 49 grams, right? Somehow we know this, the machinery that's used, we know the variance that'll be, we know the population variance for this production process, okay? We sample 49 of the pucks from, like, the assembly line, and we find a sample mean of 7.5 grams. Well, maybe we have a contract with, I don't know, the NHL or something, and they want us to be able to verify that, you know, the weight of these hockey pucks is within, you know, is equal to a certain amount. And so we want to build a 99% confidence interval where we can tell them, well, look, based off the sample we took off the assembly line, all of our hockey pucks are within this range. With 99% confidence, the true mean is somewhere within this range, okay? So what are the things that we want to identify here? Well, first of all, our sample mean, that's what we're building the confidence interval around, right? So we'll take that 7.5 and we're going to go a certain amount of standard deviations above and below it to get our lower and upper bound, okay? We also are given our population variance of 49. The final thing that we need to look at, we also have a sample size of 49, right? We sampled 49 pucks, so just kind of make it easier in this first example. If I'm looking at the 99% confidence interval, what's my alpha here? 0.01, right? Remember, alpha is the decimal form of whatever percent is outside my interval, right? Or the probability I see kind of something outside that interval, right? So 0.01, but I have an area on the right and an area on the left of my confidence interval. So if the total area on either side is 0.01, the total area on either side is 0.01, I know half of it's on the left and half of it's on the right. So I'll take that alpha, divide it by 2. 0.01 divided by 2 is 0.005. Look that value up in my table to get that z-score I need, all right? So I write down everything that I need. So I'm going to need the sample mean, my sample size, my sample variance. I'm then going to have to identify alpha. These three are usually pretty easy to identify from a problem. This one, we're kind of not familiar with it yet, but hopefully it gets easier as we go through more examples. So the z-score that we want will be for alpha over 2. So 0.01 divided by 2 is 0.005. We could then find the intermediate step, find that standard deviation of our sample means, right? And that's just a matter of plugging everything in, right? So I'll have my sample mean. I've already calculated the standard deviation of my sample means. And then it's just a matter of looking up that z-score that corresponds to 0.01 divided by 2, or 0.005, right? So we have identified those things. We want the z-score for 0.005, right? So let me show you one problem if I do this. If I go to 0.005, that was the area I wanted in the tail. That was alpha over 2. So I look here, looks like it's right in between these two. So negative 2.57, negative 2.58. That's fine, right? But if I try to plug into this equation, negative 2.58, it's going to flip it so that my lower bound actually ends up being higher than my upper bound. So we can use that standard normal table to look up what z-score we want. But remember, what we're doing is going a certain number of standard deviations above and below, right? So the negative sign and the positive sign are already built in there to our lower upper bound equation. So when I use the table to look up that z-score, well, if I'm looking up alpha values of 0.01, 0.05, 0.05, those are always going to be negative z values, right? Because I'm looking at this left side. I'm looking up at like low alpha values, right? For at least the 3 benchmark values I've told you. I'm always going to find a negative z-score. But that's already built into my equation because when I was looking up this area, remember, there was actually also an area over here that had 0.005 in it as well. So when I look up alpha over 2, I'll find the negative z-score for my lower bound. And then if I use the positive value of that z-score, that would be for my upper bound. But that's already built into the equation that we have right here. So I just look up alpha over 2. I just have to remember, I really just want the absolute value of that, the z value I find, okay? So once we kind of looked that up, found it was 2.58. Well, it was in between negative 2.57, negative 2.58. We only need the absolute value of it, so we'll take the higher of the two, higher in absolute value, 2.58. Notice I wrote here, we could have also looked up 0.995. Why? Well, because we know that if we were trying to kind of find this guy, if I want 0.005 in the upper right tail, what area would be to the left of that? Just 1 minus that, which is 0.995, okay? So just different ways of kind of thinking about the same thing. But once we have that z value, now it's just, we can do the intermediate step, which is to find the standard deviation of my sample mean. We know the equation for that standard deviation of my sample mean is equal to this. It's just a matter of plugging in the values I was given. Now that I've got my z-score, my standard deviation of my sample means, and the sample mean itself, it's just a matter of plugging them into that equation, right? So really the key to confidence intervals, we're going to be given most of this information in the problems that you see. The real key is being able to identify what is alpha, and then using that alpha, divide it by 2, and look up and find the corresponding z-score in the table, okay? Any questions on that one before we keep moving? Yeah.
So what's when you have to multiply it times the standard deviation, why do you have to do that?
So if we go all the way back here, right? We only knew that there was 95% of the sample means we could see would be within 1.96 standard deviations, right? Now, when I look up the z-score, it just looks like 1.96. But remember, the z-score interpretation is 1.96 standard deviations away, right? So if I want to translate that z-score into an actual value for the variable x I was looking at, that's why I have to multiply it by the standard deviation, right? If I was just to go 1.96 standard deviation, or 1.96, just use that z-score every time, well, that's not going to make a lot of sense for income. I just go $1.96. I need to factor in, well, the z-score is telling me how many standard deviations away I am, right? And the standard deviations, I'm looking at the distribution of sample means, so I need to multiply that 1.96 times the standard deviation of this variable, the sample mean, the distribution for the sample mean that I'm looking at. Does that make a little more sense? Okay. All right, where are we at? So we had this one. Nope, I skipped one. There we go. All right, so let's think about another example here. So let's say we went back and looked at that birth data from last week. We took a sample of 81 births. We know this population variance on the length of a pregnancy is 9 weeks. We find that the average of these 81 births, the sample mean, is 38. What would the 95% confidence interval be for kind of what the true gestation weeks or length of the pregnancy is? Well, what are the things we need to identify? We need our sample mean, we got 38. We need our population variance and our sample size. So my population variance here is 9. My sample size, I sampled 81 births, so 81. And then I want a 95% confidence interval. So the fourth thing I have to identify in these problems is going to be, what is my alpha? Okay. So if my alpha here for the 95% confidence interval should be what? 0.05, right? What percent is outside the interval? 5% in decimal form, 0.05. Okay. So I've got an alpha of 0.05. So those are the 4 things I need just to start my problem. Identify those 4 components. Now, if I look at these values, I don't think there's any I can rule out here. But if I ever give you an answer here, like let's say instead, let's say this one, where is it here? This one, let's say it was 42.12 to 43.88. So if the lower bound was 42 instead of 32 here, why could you rule that out right away? If the sample mean is 38, your confidence interval is built around that sample mean. So your confidence interval has to include 38 here. Not only does it have to include 38, what if I gave you an example like, oops, I don't want to do that, sorry. There we go. What if I had said, I'll keep the numbers round here so it's easy. So 37 and 42. Why do I know that can't be my confidence interval? Yeah, I have to go the same number of standard deviations above and below the mean. So when I look at my lower and upper bound, it better be the same distance from that sample mean I found. Okay? And we don't have any answers here that really fit that criterion, so all these are valid. So we actually have to kind of work through this, right? So we identified the piece of information we needed. I then look up the z-score for alpha over 2. Well, if alpha is 0.05, alpha divided by 2 would be 0.025. So I go to my table. I'm looking up the area in the tail that I want. So I try to find 0.025. I scroll down here. It's exactly in the table, so this is a nice one. Negative 1.96. Right? Now we said it's negative, but that's because I'm looking at that kind of lower bound, right? So I don't need to include the negative sign. I just need that z value, the absolute value, so 1.96. So we just looked up, we found that 1.96. I then can calculate my intermediate kind of value of the standard deviation for my sample means using this equation, plug in my population variance, my sample size. Now I'll just plug everything in here, right? Now, I wrote this out a little bit differently here, right? So I could just plug in the 1/3 because I know I'm multiplying that z value by the standard deviations, or sorry, by the standard deviation of my sample mean. The reason why I wrote it out this way as well is because I don't have to find the intermediate step, right? I can go ahead and plug all my values into this equation and find the lower and upper bound as well without kind of doing that intermediate step. Also, another way that we said we could write this mathematically, I take the square root of something, it cancels, and then I have the square root of n there, and that's what appears in the slide. So we can start seeing this in multiple forms, right? And it's because really what this represented was what we were calculating in that intermediate step, which is just the standard deviation of my sample means. So whatever way is easier for you, if first calculating this and then just plugging in that one value, that's fine. Or kind of having the entire confidence interval equation written out with the equation for the standard deviation of our sample means kind of plugged into it. Does that make sense? Are there any questions on that? So really, it's just kind of, once we get to that point, it's a matter of plugging those things into our calculator, right? So what I could say in this example is, with 95% confidence, the true length of pregnancy is somewhere between 87.3 and 38.6 weeks. Right? If I go back here, just so we get some interpretation for the hockey puck one, kind of forgot to mention, this would be like with 99% confidence, I can tell you the mean weight for the hockey puck is somewhere in between what, about 5 and 10 grams. That seems not good. That seems like not something I'd want to go to someone I'm trying to create a product for and tell them that, right? And the reason really here is why is because, you know, we had a pretty high population variance, right? 49 grams is pretty high when the average is only 7. Right? So, you know, we can start thinking about the interpretation of these confidence intervals as well. Where are we on time here? 5 minutes? Okay. What do I want to do here? Let me see where we can pick up next. Okay, so I want to do that next class. I'll skip this example. This might be a good one to kind of work through on your own. It's kind of a fun one. Like you can kind of think about, you know, if I'm trying to create a product and I want it to weigh a certain amount, kind of like the hockey puck one, but here I have kind of a specific. I know that it should weigh 45 pounds. So the example is like if I went over to the rec center, got what, 35, you know, 45-pound plates. I find that the sample mean is 46.5. Well, it still could be that the true population mean is 45, right? But based off my sample, I can build a confidence interval. If I do that, and that confidence interval at the 90% level doesn't include 45 pounds, well, that company probably cares, right? I mean, it's kind of an arbitrary example if it's, you know, metal weights over at the gym, right? Because, okay, with 90% confidence, I can tell you your product doesn't weigh what you think it does. Well, who cares if someone's putting a little bit of extra weight on whatever they're doing? Well, this is a huge problem if, I don't know, it's a steel beam supporting a building or something, you know, like this is like really important in a lot of other examples when you have a product that you need to weigh a certain amount. If you take a sample from your assembly line or, you know, something, and you find that your confidence interval doesn't include what that weight you need it to be is, we got problems, right? So that's kind of an example you could work through on your own, just with some different values. You know, it's the same kind of thing the other two examples that we worked through, okay? So I want to show you one thing, and we'll probably, maybe I'll revisit this next class when we get through a few more examples, so maybe it'll resonate more. So I had this like old data, and I wanted to kind of prove that these confidence intervals are doing what we did, when I say they are doing, right? So I've got all these different letter grades, right, for everyone who's ever taken a stats course from me, and then I just identified them with a number, right? So in Excel, I can find what the true mean actually is, right? I have the population data. I then did, right, here's samples. I randomly generated some numbers, did some VLOOKUP stuff. You don't need to know about any of this, but these are essentially 1,000 different samples of size 50, right? So I've got 1,000 samples. That counted the number of samples I had. They're all sample size 50. From each one of those samples, I then found the sample mean. I then put in this equation for the lower bound, which is take that sample mean, subtract, and this is where I'll revisit this next class. We'll do some more work in Excel. You can use that norm.s.inv just like we were using the table. So look up alpha over 2, or 1 minus that, because I want to make sure I'm getting a positive z value there. I can then take the square root of the original population variance over my sample size. I'll do the same thing for the upper bound, but I'll add that margin of error. What I then did is a little if statement that said, look, if my lower upper bound doesn't include this value, right? If it's either that 79 is below the lower bound or if it's above the upper bound, put a 1, right? I then counted the number of confidence intervals that included the sample, the true population mean. So 953 did here out of 1,000, or about 95.3%. Well, that should be my 95% confidence interval, right? Now it's a little bit off here, and notice like if I click on a cell, the numbers change. So it's always kind of floating around 95%. And that's because in theory, I don't need 1,000 of these samples. I would actually need an infinite number of these samples to get it to be exactly 95%. You know, just using a little data experiment like this, you can see if I took 1,000, yeah, almost always, whoops, about 95%, I want these numbers to change, there we go. Always about 95% do include that true population mean. Now, we usually don't have the population data, so we usually can't do this, but this is kind of a fun little thing to kind of prove to yourself. So next class, we'll do some more Excel work. We'll also start to do confidence intervals for proportions, right? And that really wraps it up for me. If you guys have any questions after class, feel free to ask. And I'll leave the Zoom open for a little bit as well.